So demand paging allows us to have more processes running in the computer system at the same time, because you bring in only the pages that are required into the memory from the swap space. But what if there are so many processes that even with demand paging, they have used all of the available memory frames? So what if there is no free frame left in memory? What happens in that case? So what we can do in that case is, as we slightly mentioned earlier, you pick a victim page that is a page that is used by some other process, or maybe even the same process, and get rid of that page. When I say get rid of, write it to the swap, so that that frame, the frame for that page, becomes available, and you can bring the new page you want from the swap space in place of that swapped out frame. That is one solution. But then the question is, how do we pick the victim frame? This is called page replacement, because you're replacing a page by another page. And if the victim pages are selected carefully, this would significantly improve the performance of the system. Otherwise, if you incorrectly select the victim page, that means, for example, you pick a victim page which would soon be used and write that page into the swap, soon you'll have another page fault. And again, if this is a bad page replacement algorithm, it will repeat the same error over and over. You won't get any errors in this, but the system performance will degrade significantly. So the page replacement algorithm prevents the over allocation of memory by modifying the page fault service routine by including some page replacement algorithm. You need to now add another bit, the modify, or the more commonly used name is the dirty bit, which shows whether the page has been modified since it was last transferred from the swap device, from the backing store, because such a page, before getting rid of it, when it is selected as the victim, should be completely from the beginning to the end. That page has to be written to the backing store. Note that you are not able to write single byte into the backing store. You have to write the whole page, even if only one byte is modified. And the reason is, we know that the page has been modified, the page is dirty, but we don't know which byte has been modified. It's not possible to keep track of the bytes that are being modified, because the cost of keeping track of that would be more than the byte itself. So in this example, for example, process P1 wants to access an instruction, for example, in page 1, because the program counter is pointing somewhere in page 1 of process 1. It was supposed to be in this entry in the page table, but we see that that entry is marked as invalid. Therefore, we need to go to the backing store, find that page. Well, this is doable, fine. But then in the physical memory, we need to find an empty, an available frame in which we could store B. Since there are no available frames here, one of them has to be selected as the victim. That could belong to the same process P1, or maybe some other process. We will discuss the pros and cons, and that will be written back to the backing store if it has been modified. Note that if that victim page has not been modified, we don't need to write it. because it is the copy in the memory and the copy on the backing store, they are the same. So if we can find, therefore, a frame that's not dirty, that's better. But if not, we will find a dirty frame and write that frame into the corresponding page in the backing store. Now that frame has become available, and the page for B in the backing store now can be copied in place of that freed frame in memory. So this is basically how the basic page replacement algorithm is working. So what's given in this slide is almost what we have already discussed. When you try to access a memory location in for which the page is not in memory, you first try to find a free frame into which you can copy the page in the backing store. But if you cannot find a free frame, then you search for a victim frame, and that victim frame is written to the backing store if it's dirty. If not, you just discard that victim frame and bring the page in the backing store in place of the victim frame. Note that this requires two operations actually here. You need two page transfers if the victim frame is dirty. One for writing the victim frame to the backing store, and the other is for reading the new frame from the backing store into the frame in memory. And doing two page transfers now increases the effective access time even further. Remember that our pages are typically between 512 kilobytes and 16 megabytes. So it's quite effective. It takes several seconds to transfer the page between the memory and the backing store. So we need, therefore, a frame allocation algorithm which will determine how many frames each process should be given. So we have some limited number of frames in the memory. How many frames to each process? Should it be same for everyone, or maybe it should be different? And which frames are to be replaced, which is done by the page replacement algorithm. In the page replacement algorithm, the basic idea is to reduce the number of page faults. We want as few page faults as possible. So you design your own page replacement algorithm. If you want, you can also come up with a new page replacement algorithm. But we need a way of assessing how good or bad a proposed page replacement algorithm is. And to do that, what you do is you generate some page access sequence, which is actually a sequence of page numbers to which you're accessing, and evaluate the performance of alternative page replacement algorithms for the same, what we call, reference string. Here, for example, we have one reference string, which is also used in the examples we have in this chapter. The assumption is we first access page 7. Now it could be several processes, but the processes in memory are accessing 7, then 0, then 1, then 2, 0 again, 3, 0 again, 4, 2, 3 again, going in this way. Now note that this is one reference string. One specific page replacement algorithm could perform very good with this reference string, but in fact, if you change the reference string, that algorithm might fail. Therefore, for a proper evaluation, you generate many such reference strings and look at the average. Okay, so each algorithm may be biased. It could perform better or worse with specific reference strings. So you should actually be running it with different reference strings and then looking at the average of that. So if you look at the number of frames available per process, for example, or in general for the whole system, if you increase the number of frames in memory, of course the number of page faults will decrease. If the number of frames in the memory is small, then when you try to access these pages, of course there's no chance you will have many page faults. For example, if you had only 3 frames in the memory, you would put 7 in frame 0, 0 in frame 1, 1 in frame 2. Then when you try to access 2, you have to pick one of these first 3, 7, 0, 1, and replace that one with 2. That means that page is not in memory anymore. Then, for example, you access 0 once again. So if the victim you had selected was 0, unfortunately, that would mean a second page fault. But if you, for example, selected 1, it would be less likely. You wouldn't have the page fault there. But later, of course, at this point, for example, you need to access 1 again. So at this point, you would have another page fault for that specific page. Also note that this reference string is something we have created, so I know what that reference string is, but normally the algorithm doesn't know the future. So in the beginning, the algorithm, when you're trying to evaluate the performance of the algorithm, you have no idea which page is going to be accessed. So you're told these references one at a time. You don't know all of them immediately at the beginning. So you cannot, it's difficult to know the future, of course. So one solution is the first in, first out algorithm. This is, of course, the first one we'd think of. So given that reference string we mentioned, initially all 3 frames would be empty. Then you access 7, so you put 7 in the first one, 0 in the second one, 1 in the third one. When you get 2, you have to pick a victim. In the first in, first out algorithm, the first one that entered this pool of frames was 7, so 7 is replaced. When you access 0, you don't make any changes because 0 is already there. But when you access 3, then you have to replace again the first one among these. 7 is already gone, so the oldest one among these is 0, so 0 is replaced by 3. Then you have another access to 0, unfortunately. So that was a very bad decision to replace 0, but we don't know the future. So now you pick 1 as the victim and replace 1 with 0. So if you run this algorithm, you can see that we have 15 page faults. As I said, if you change the reference string, the result would be difficult. So the basic idea, as we mentioned earlier, is as the number of frames increases, we would expect fewer page faults, right? For example, instead of 3 available slots here, if I had, let's say, 6 available slots, I would be expecting fewer page faults, right? However, when you try that, you will see that with FIFO, you experience what we call Belady's anomaly. Belady's anomaly is, as I said, yes, as the number of frames increases, we would expect a graph like this, but unfortunately we see a graph like this. Sometimes it doesn't change, but more important, like if you go from 3 frames to 4 frames, it's very interesting that the number of page faults is actually increasing. And this is just because of the FIFO order and the corresponding reference string. So depending on the reference string, sometimes in FIFO algorithm, you might experience Belady's anomaly, which is really an anomaly, something unexpected. So it's like you're reserving more memory for this, or maybe you're buying more memory to improve the performance, but it gets worse. So that's something, of course, you don't like. Now, what is the optimal solution? The optimal solution would be knowing the future, which is actually impossible, but let's assume that we magically knew the future. So remember the problem we had with 0 here? I had replaced 0 with 3, but then I accessed 0 once again, so it caused another page fault. So if I had known the future, I would have performed better. Like in the first 3 accesses, references, okay, it's obvious, you should place 7, 0, 1 in this order. When 2 comes in, if I know the future, I can look at the future accesses and see I need to access. Now, what do I have in the frames? I have 7, 0, and 1. Which one is furthest in the future? Replace that one. Don't replace one that will soon be needed. I can see that soon I will need 0. So 0 is not an option. I shouldn't be replacing 0. I shouldn't be replacing 1 either, because 1 also is accessed at some point in the future. 7 is accessed in a very far future. So among 7, 0, and 1, 7 is the one that's to be accessed latest, so it's better to replace 7 with 2. For 0, it's already in memory, so no need to do anything. When I need to place 3, now again, among 2, 0, and 1, which one is the latest to be accessed? 0 is immediately going to be accessed, so I'm not going to replace 0. That's the problem we had with FIFO. 4, anyways, 4 is not among 2, 0, 1, that's not to be considered. 2 is also to be accessed, so no need to look further. 1 is the furthest in time, so I replace 1 with 3. So it goes this way. So for the optimal algorithm, I need only 9 page faults. I experience 9 page faults rather than 15 in the case of FIFO. Now, once again, this is the optimal algorithm. It knows the future, which is not possible. Why do we have the optimal algorithm? The optimal algorithm says you cannot do any better than 9. That means it's not possible to solve this problem with no page faults, or 1 or 2 or 3 page faults. Minimum is 9 page faults. So if you come up with an algorithm, for example, that solves this problem, let's say with 10 page faults, you're very close to optimal. Well, if you want, you can try to improve the algorithm better, but there is little room for improvement. Maybe you don't need to pay more time, more effort to improve it. If you achieve 9, just stop improving, because you cannot do any better theoretically. So optimal algorithm is used just for comparison. We don't really have the optimal algorithm in real life. Another alternative is the least recently used algorithm. The basic idea is if you have not been accessing a page for some time, it is probably you're not interested in that page anymore. That means the program you're running is now executing instructions and functions that are not related to the early accesses. For example, in the beginning of your program, you could be, for example, initializing the variables. So there are some functions and instructions that are used for initializing the variables. After you're done with the initializations, you will never call those functions again because they're already initialized. So those algorithms will not be accessed for a long time. Actually, never in the future. But if you're looking at time t, at any point time t, you see that it's been a long time since you accessed those functions. And if you need space, if you need some free frame, it's likely that you're not going to use it because you haven't been using it for a long time. This is just like, for example, if you look at the, the songs that you have been listening to in, say, your CD collection, or of course nowadays in Spotify, there could be songs that you were listening to, say, 5 years ago, but you're not interested in them anymore because your taste of music has changed in those 5 years. So the probability of those songs being played is less likely. So if you have, for example, limited storage space, say on your phone, the ones that should be removed from the cache would be the songs that have not been played for a long time. So that's the idea with the least recently used. Now note that there is no guarantee that this will happen. We're just trying to increase our chances. So the same reference string apply least recently used instead of FIFO, you get 12 faults, page faults. Now we know that it couldn't be any better than 9. So least recently used, in other words, is between FIFO and optimal. Nothing can be better than optimal, we know that. But least recently used performs better than FIFO because it at least has a logic. It's not like FIFO, which is just first in, first out. But how do you implement the least recently used algorithm? One possible implementation is with each page you have a counter, and whenever you access the page, in that counter you store the time. So you copy the clock into that counter. So when you need to find the one which has not been accessed for the longest duration, look at those counter values. Since the counter contains the last access time, the smallest counter value is the one that has been accessed further in the past. So you can just replace that one. But this, note that, requires searching through a table. An alternative implementation is you keep a stack. So the least, the most frequent, the most recently accessed page would be at the top of the stack, and the least recently used access, the least recently used would be at the bottom of the stack, because every time you access a page, you remove it from where it was and putting it back to the top. So you're always bringing the one that's recently used back to the top. This is difficult to implement with the stack itself, because to pick something from the middle, you have to pop all the ones above to somewhere else, take that one out, and then push all of them back in. Instead of that, you can make use of a double linked list, which will perform better. But moving to the top would require 6 pointer updates in the worst case. So updating has become more expensive because you have to update 6 pointers. But for searching, you don't need to search at all. Just always get the top. You're not doing any searching. Least recently used and optimal are cases of these stack algorithms that don't have the Belady's anomaly effect. Now there are some alternative solutions that are not least recently used, but they're approximations to least recently used. because least recently used typically requires some special hardware and it's also slow. So one alternative is making use of the reference bit. Instead of storing a large counter, you just store 1 bit per page, which is initially 0, and every time the page is accessed, you make it 1. Whenever you need a page for replacement, you try to find one which has reference bit 0, assuming since it has not been accessed, and replace that one if one like that ever occurs, of course. Note that in this case we are not looking at the order because we don't know the order. We have not stored the time. We just know these pages have been accessed, these have not. Okay, so of course there should also be something that once in a while, for example, resetting all of them back to 0. An alternative approach, again an approximation to LRU, is a second chance algorithm. So the idea is, in the second chance algorithm, you're still working as in FIFO, but you have again the reference bit. If the reference bit is 0, that means the page has not been accessed for some time, just pick that one as the victim. So in that sense, it's easy. If the reference bit is 1, you don't do the replacement, but you're also clearing the reference bit of that page to 0 and going into the next one. So in other words, you're giving a second chance to the pages with the reference bit set to 1 by not replacing them immediately, but also you're resetting their reference bit so that next time I come there, if it has been accessed till the next time I come to the same page again, okay, it is again safe. But if it has not been replaced until next time I come to the same page, then that means that page is not being used frequently. It was used sometime in the past, but not anymore. So now it can be selected as the victim. So the second chance algorithm works as follows. Let's say the next victim to be selected will be this one, but its reference bit is set to 1. So you reset it to 0, but you don't do the replacement with that one. You go to the next one. That also has the reference bit set to 1. Also reset that one to 0. Then go to the next one. That one's reference bit is 0. So pick that one. Okay. So this is the page to be replaced. The previous 2 pages have not been replaced, but note that their reference bits have been reset. Next time I need to find a victim, I will be looking into this one. Again, give a second chance to that one and make or reset its reference bit. Give a second chance to this one, reset it to 0. Come to this one, and this will be selected as a victim the next time. Meanwhile, these 2 bits, remember, these 2 pages were given a second chance. If, for example, this one was accessed, meanwhile, its reference bit will be set to 1 again. So next time this is to be considered as the victim, again it will be safe because its reference bit has been set to 1. But if this page, after it was reset to 0, if this page was not accessed at all, that page has been given a second chance, and unfortunately it didn't use it. So it would be selected as the next victim. Now there are some enhancements also into the second chance algorithm. You can improve the second chance algorithm by adding a second bit, the modify bit. Actually, we already have the modify or dirty bit, remember. So look at the reference bit and the modify bit together as a tuple. If that tuple is 0, 0 or 0, 1, 1, 0 or 1, 1, it has different meanings. If it's 0, 0, that means this page has not been accessed recently, and also it has not been modified. That means if you select it as the victim, first of all, you don't need to write it. You can just discard it simply. So we avoid one page copy operation to the swap space. So the cost of selecting that page as the victim is low, in other words. And also, since it has not been accessed recently, it is a good candidate. It's almost, not guaranteed, but it's almost the least recently used algorithm, the least recently used page, I'm sorry. The other case is 0, 1. Again, the page has not been used for some time, so it is a candidate for replacement. However, it has been modified to 1. So the dirty bit is 1. So, well, if I am really running out of free space, if I don't have pages with 0, 0, 0, 1 would be next candidate. But note that it incurs the cost of writing the page to the swap. So it's a little bit more costly compared to case 1. Case 3 is worse than cases 1 and 2. The page has been used recently, so it is likely that it will be used again. However, at least it doesn't have a cost. It's not modified. So I would like to keep the page because I guess this page will be required. If I pick this page as the victim, the probability that soon I will be needing it is high. So, okay, writing it to the swap does not require a write operation. However, if I pick this one as the victim, later I need to read it from the swap. So there's still a cost of reading one full page. So that's why this is in the third order. I wouldn't prefer this one over the previous two. And the last one is the worst one. The page is frequently being used, and also it has been modified. So it has a cost of writing to the swap. Also, probably I will soon need it. So this is the last one to be picked. So when the page replacement algorithm is called, it would be picking a page from these classes, first trying to find some page in the first class, if not second, not third, finally the fourth. And this would be done typically in a circular queue, and to find one you might need to go over that circular queue several times. You can, for example, keep a counter of the number of references that have been accessed. So this way actually you are recording not only the last time, but you're also looking at how many times the page is being used. So how frequently am I using that page? These counting algorithms are not very common, but if you use it, you have two options. One is the least frequently used algorithm. So it will replace the page with the smallest count. It says this page is not being frequently used, so you guess it won't be used in the future. Of course, this is again a guess, might be true or false. The alternative is just the inverse, most frequently used. It's based on the idea that the least frequently used are the ones that have just been brought into the memory, so they didn't have the chance to be accessed. The pages that have been accessed most frequently probably have been in the memory for a long time, so hopefully you're not going to use them anymore because they have been used a lot, hopefully, in the past. Of course, once again, these are assumptions, might hold or may not. But as I said, the counting algorithms are not frequently used, frequently implemented, sorry. Now, there are still alternatives these are improvements to the previous algorithms. So not replacing those algorithms, but these are in addition to the previous approaches. Like, for example, you can keep a pool of free frames. Then when a frame is needed, there is one available in the free frames pool, so you can pick one from there. If not, if the free frames pool is empty, then you need to find a victim. You can read the page into the free frame and select the victim to evict, and then that one goes into the pool. What I mean is the following. Let me phrase it in a better way. When there's a page fault, you go to the pool of free frames. They are already free. You pick one from there and use it. And meanwhile, you find a victim. While other things are going on, you make that you write the victim page to the swap, so it becomes available now, and that page is placed into the free pool. So this way, you always have a pool of free frames. So when you need a frame, you don't need to wait. So the process can immediately resume because you have some free frame. But of course, in this way, the pool of free frames will be emptied. For it not to be emptied, whenever you have time, you pick some victims and enrich the pool of free frames. One other approach is keeping list of modified frames, the ones that are marked as dirty, and when the backing store, that swap device, is idle, it's not doing anything, in the background just write the page to the swap so that it is not dirty anymore. So in other words, whenever you have time, you clean the dirty pages. By cleaning the dirty page, I mean you're synchronizing the copy in the swap and in memory. You're copying from the memory into the swap whenever you have time, whenever the swap device is free, so that in the future, when you need to find a page which is not modified, you already have it. So this, for example, was modified, but when the swap space was idle, when the swap disk was idle, you would write it to the swap. Thus, it would move from class 2 to class 1. So you would be increasing the number of pages in class 1. Or similarly, a page that's even modified could be written to the swap device or not. But doing this would be less effective than doing this. So I would typically prefer moving something from class 2 to class 1. Or you can keep frame. No, the last one is the following idea. You have selected a page to be like in the first one. You have selected a page as the victim, and you have written it to the swap, okay, and moved that page to the free pool. Note that I haven't read anything into it yet. I just selected as the victim. I have copied everything to the swap, and now I have marked this frame as free. So it's now in the free pool. If a process needs some free frame, this could be used. Now, if that page I had selected as the victim happens to be accessed, which means my selection as the victim was not a very good idea. That was my mistake. So it's a wrong victim selection. If that happens, I don't need to read it from the swap because the content is still intact. The content is still the same. I haven't written anything on it. I just said it's free now, but the content is still there. Since I'm not erasing all bits in the page, it's still the same. So I can easily reclaim it from the free pool and use it. Okay, so this is the idea. This is helping if by chance we make a wrong selection for the victim. For example, in Linux, this is being used. Now, all of these algorithms have the operating system guess about the future, which is difficult. We make some guesses like least recently used and others, but the probability of page faults is still there. However, there are some cases for some specific applications like the databases. They have some better knowledge of what they're going to need. So the application actually knows what it will need because the database system knows which records it will be using or which records are related to each other. So wherever they are stored on the disk, it knows that if you access this one, because of the database relationships, these two pages will also be required. Okay, so the database has a better knowledge of the relationships between the pages. However, from the operating system's point of view, since the operating system is implementing a very generic idea, because with the operating system you could be running the editors, the web browsers, any services, and the database systems, user applications, all of them. So the operating system does not make use of such information because it doesn't have that information from the applications, but the application within itself may know it, not your applications. Your applications typically don't know where things are being replaced, but the database might say, the database system might say, just leave it to me. I can manage it better than the operating system because I know what I'm doing. Of course, those database systems are very sophisticated softwares. So for such applications, it might be better to let the application manage its own disk space. That is one case. The other one is the memory intensive application can cause double buffering. The idea is the following. You want to read something from a file. You first read into kernel space. Then from the kernel space, it's copied into the user space. So if you read file, let's say F1, if as another user or as another application, I also need to read the same part of that same file, F1, if it was directly brought to your memory space, I wouldn't be able to read it because it's in your memory address space, not mine, if we're not sharing a shared memory. However, if it's brought into the operating system buffers, it is copied into the buffers once, and I would be just reading not from the disk anymore, but from the I/O buffer because it's already brought in. However, note that this now the probability of this happening is not, of course, very high, but this requires two copy operations from the disk to the OS buffer, from the OS buffer to the user buffer. So this is what's called double buffering, and you keep two copies of the same thing actually, one in the kernel space and one in the user space. And the applications keep the page in memory for its own work also. So for these reasons, it might be better to allow some specific applications, not all. For most applications, it's still better to work through the operating system itself. But for some specific applications, you might want to allow what's called raw disk mode. That means some partition is marked as raw access, and you just leave it to the application. So the operating system gives special permissions to such processes, specifically for those file systems, to have raw access. That means bypass the operating system's mechanisms. It can just manage it by itself.